I've set up the Rigel DSA815-TG spectrum analyzer with tracking generator to sweep a 2-meter amateur band compact filter. This is just a bandpass filter. It uses 2 links to link to a central core in the middle here that is basically a quarter wave electrically section of coax in a high Q fashion air dielectric cavity. It has the center that can be tuned back and forth, and it has a couple of links here that can be tuned. Those links look something like this, and are inside the inside like this, next to the core here, or the rod that's in there. It's all set up so that the temperature coefficient of this rod here is equal and opposite to what this aluminum cavity is, so that over temperature it will maintain the same physical relationships and thus not move in frequency very much. Now I've linked in and linked out, and this is the curve we have. As you see, the skirts are not real steep. We're tracking from 140, which is near the lower end of this, to 150 megahertz. And we're at, according to the peak here, let's get the marker 4 turned off here. Okay, go back to marker 1. According to the peak here, we're at about 2.5 dB down, which is a little bit more than we would like to see for this kind of a filter, because the likelihood is that the match on this at 2.5 dB is not going to be as good as we'd like to see it. We'll cover how to check that in a future video. But anyway, so to show you how this can be tuned over a wide range, I'll take a tuning tool. Now, you say that's sort of a strange tuning tool, but in this case we have a little acorn on the end of this. This is typical of Telewave type cavities. I've already loosened this nut so that it's able to turn freely, and this happens to be the size to turn that. So if I put it on here, let's move it over. You can see I can move the frequency quite a little ways. By the way, notice what's happening with this particular unit. This is one we got from the back room. And as I tune it, and I was tuning one direction there, I'll flip it to the other direction. Notice the hesitation there every once in a while. Somebody's dropped this thing at some point, and I think the rod that's inside there is bent, so you'll see it go and that just means it is bent, and this probably should be replaced, the center assembly. This was one that was used in field service where it was moved around a lot and changed in frequency a lot, so that's probably why it has this this problem. But anyway, the point is it shows you how you can rough tune these things fairly quickly. Let's go down to the bottom here. So we got down to 140 now. Let's flip this thing and go the other direction, and we'll go up to however high it goes here. Whoops. Oh, I think I ran into the end there. Actually, what happened was this this nut cinched down, but let's see where that is. So this actually, it's up around 148.283, so it should get up to 150. But this nut got in our way, and I have the tool for that. And that's your standard spanner, as the British like to say, or crescent wrench. Let's loosen that thing up a little and wind it up to the top here so we can go a little further. And we'll show you that it goes up to about 150. Okay, so we went up to 150. So you notice that this didn't change much in level all the way up there. Let's hit the peak again. We're still pointed at 2.35 up here. We were at 2.4, I think, there, or 4.5. So let's go back down to where we wanted to be. Let's make this right at 144.1. First, what we'd want to do is set the marker frequency to 144.1 megahertz. And it happened to put it right on that, so we have enough resolution in the screen to do this. All right, and then for the fine tuning, this little puppy is probably the best tool. We're at minus 2.62 at that frequency. That can be adjusted now by using these two links and just loosening these screws and rotating it slightly. So let me do that. But to show you what does happen as you reduce the loss through this thing, I will save that. We'll go to Trace here, save Trace 1. By going freeze. So now that's going to stay there. We'll go to Trace 2, which is now blank. We'll go to clear right on that trace. Now it's showing you the same curve right on top of the other curve. You can't see the other ones because this one is in front of it. But if I do this, you'll see, if I can get it on here correctly, that as I go off the frequency, and you see that the resolution here is pretty good in terms of tuning. Okay, so now you see that we're over here at a peak of 144.233. Okay, and we have a little less loss at that frequency as well. So that's the basic tuning in that regard. If we now take a look at this thing, we can take this cavity and tune it, but not, yeah, there we go. And loosen this a little bit. Unloosen that a little bit. Unloosen this one a little bit. Not always that easy to. Let's see if we can do this. And first let's tweak this back on the same frequency so we see what happens. All right, our curves are synchronized at the moment. And as we tune this thing, you'll see that my loss will change. There I have more loss, and you can see the skirts tighten up. However, at 5 dB of loss, the likelihood is there's not much of a match. So let's go back up here. And let's bring this up so it's not quite the same Q, which means the loss will be less. And we'll tighten it down there. We probably only need to tighten one for this purpose. And as you see, our skirts are less. And we'll hit the peak here again. We've gone to 2.91. So we've actually gone up in loss. However, this one is no longer tweaked up quite the same. Now you can see I can go down pretty far. Aha, I can go up pretty far too here. Let's hit the peak here. Let's put this back at 144.1 because that's where we really want to be. 144.1 megahertz. All right. Well, now we have less loss than we had before. I'll tighten that down. All right. And now we need to tweak this up tuning wise. All right, we're at 1.5 dB now of loss, which is a fairly typical medium loss for a cavity, 1.5 dB. And we'll hit the peak and make sure we're actually a little high in frequency, so we could go to 144.1 again megahertz and tweak up the frequency just a little bit more here. And now to help this, and it turns out that it doesn't cause any problem for the tracking generator, go to amplitude, scale per division. Instead of 10 dB, let's make this 5. It'll be much easier to see what we're doing here. Ah yes, now you can see the difference between our original one here and where we are now. Okay. And as you see, the calibration's still there. This is still 10 dB down from the top, etc. There's no change because that's merely a scale change and doesn't affect the tracking generator at all. Oh, we want to look at the marker level here. Okay, it looks like we're pretty close to where the marker wants to peak. 154, yeah, right about in there. Now, if I was done with this, I would tighten up these screws again, and I would bring this down and tighten it up, and then if I needed to, make some final adjustments. But that's how you tune up a bandpass filter, and it's fairly straightforward, no real problems doing it. We've gone from what we were on before on this at a level of about -2.5, I think it was, 2.4, whatever it was, to 1. And let's find out what our 3 dB point is. So we would go to delta on that and go down 3 dB. 3.05, it's good enough. So that's 316 kilohertz down, it's 3 dB down. And three dB down at 333 kilohertz on the high side. Let's look at the 20 dB point. Now let's make it 10 dB first. So at about a megahertz away, you're down 10 dB, which will help with anything that's above us or below us. Whether this is a transmit filter or receive filter, any signals coming into a receiver will be knocked down by 10 dB at 900, let's call it a megahertz. And any noise that the transmitter going through this thing would also be down 10 dB. Let's go to 20 dB, which should be out here somewhere. There we go. So at about 3 megahertz away, you're down 20 dB. So 144.1, 3 megahertz away is 147.1. So all that repeaters up in the 147 range here would be knocked down at least 20 dB. And any commercial stuff up right above the 2 meter band would also, as well as on the low side, down in the bands down around 3 or 4 megahertz below the 2 meter band. So 2 of these would have the slope about twice what that is. So they'd go down a lot faster and come down here. So as you can see, you can put several of these filters together and make a fairly good pass band. You can have this at much less loss than this as well. You can probably make this filter go down to a half a dB and still have a fairly decent curve, even though it's a compact. A larger cavity, and this one's only, I don't know, let's see what it is. Cavity is about 11 inches long, 11 and a half. Well, actually with all this, about 15 inches. Okay. Compared to your usual quarter wave cavity, which I'll show you one of here. This is one that was built for a linear translator we used to have in the Bay Area, and you can see it's more than twice as long as the other cavity here. So that's the difference in size between a full size and a compact cavity. And the Q, of course, on this cavity would be much better. Another kind of cavity commonly used in radio circuits to control intermodulation, cross-modulation, and desensing and transmitter noise from getting from one transmitter in a system to another one in the same tower, say, is the pass notch or pass reject filter and the notch filter. They're both essentially the same item. One just has a capacitor for resonating the loop to provide a notch that's controllable, and the other one just has a loop like I showed you earlier, this loop, which has no capacitor on it, as you can see. It's just blank. So it'll just act as a notch if this one's inserted. But if the one that's on here is inserted, you see that it has a capacitor right here. And that capacitor can be tuned to resonate the loop that's in here to notch out a given frequency while this passes a different frequency. That's what's used in a duplexer for a pass reject type duplexer. Here we have the cables, and I put a T on here because that's what goes on to here. I have not got the tracking generator on. I've used the preamp inside of this unit to get the noise floor down around minus 78 dBm here. And if I turn on the tracking generator here, you'll see it rises a little bit, but across this band, at least from 140 to 150, we don't have near as much leakage problem as on some of the higher frequencies with this unit. And that's fine. That's more than 70 dB of dynamic range. Okay, and then the other thing we need to do is normalize the signal. So we would put this thing together like this, turn off the hit normalize, turn off the original normalization, and then store the reference, and then hit normalize again. You have to sometimes hold that thing. And now it's set up on 0 here and drop down a little bit. I've got this in the middle, so I'll hit System and Display and Active Function I'll put in the center. That way we'll have a little better situation between the text and the traces here. Then we'll go back to tracking generator. Our level is 0 dBm on the tracking generator. And hit normalize again. Turn it off. Turn it on. We're right back where we were before. And now if I put that on here, we should see the resonance of this unit. With end connectors, it's best to put a little pressure square on them, and then you'll see it'll be easier to screw on. All right, so here we have the T, and we see the resonance here, and see we see the notch here. The notch looks to be about 20. Well, let's find out. First, we hit the peak. It finds that at 145/200, which is, I believe, is where I tuned this to. And we'll see that the loss is about 0.74 dB. And if I use this screwdriver, or better yet, a tuning tool, I don't happen to have one at the moment, I can go into this slot on this thing and I can tune that notch different places. So let's, if 200 is it here, we want 600 kilohertz, let's say below that. So that would be 144, 400. So let's turn on a different marker. Marker 2, turn it on. Let's go 144.400 megahertz. All right, it's right there. This is obviously higher, and so we'll tune it right onto that and see what we get for a notch. Now you notice as we go further away, we get a deeper notch. It's 30.5 dB down from this peak, or actually from 0 here. And 144/400 is where it's at. Now let's say we wanted a megahertz, so that'd be 144/200. Let's hit the marker, and we'll go 144.2000 megahertz. All right. So let's see what happens if I move that notch there for a 1 megahertz split. Aha, even more notch depth. So we got 33.5 dB below this peak, and the peak, as I recall, was, well, let's find out. The peak was 0.75 down. Now, again, you have these 3 screws, and you can rotate this to change this loss up and down. And I may not be exactly on the peak for 144/200, so let's go to marker 2 again, and let's find out. This is hard to do with just your fingers, so I'll use the tweaky tool here. Oh, we want 145/200. Let's see where the actual minimum is there. Now you're probably hearing the squeakiness of this thing as I tune it. That's probably why it was in the back room. It's been played with hard. Let's put it that way. So minus 0.66 seems to be the 76 seems to be the place where this thing is peaked. And so there you go for a 1 meg split. And the other thing I'd like to point out to you is, if you notice, this goes down here, but it comes back up here to only about 8 dB. Let's put marker 3 over there, down at 140. And then marker 4 we'll put over here on the other side. Again, turn it on. and it comes down to about 10 dB at 150. So this kind of a filter doesn't have the characteristics of the bandpass filter where it goes down and continues to go down. That's why in the case of mountaintop locations where there's a lot of transmitters, a duplexer alone is not always the answer to what you need to do, because you're only rejecting these frequencies on either the transmitter or the receiver. Transmit noise if the transmitter happens to be here, or if the transmitter happens to be here, it's notching the transmitter relative to the receiver, which is here. But anything up in here, anything down in here has some attenuation, but not as much as you might like. So a pair of these will give you the notch that you need down to around 70 to 80 dB. 3 of them certainly give you about 100 dB, and that will take care of most things. But the other thing, and these of course will be a little lower, but if you really want the best performance, you may also need a bandpass filter to bring down everything outside of the area here you're trying to receive or transmit in. So that's something to consider. So 2 cavities pass reject and 1 cavity bandpass on each side is probably the best solution to modern day sites where there's a lot of transmitters and receivers, especially if you have a bunch of people who have duplexers instead of combiners. See, most combiners for transmitters have selectivity, and the selectivity is a bandpass, therefore it goes down and down and down. Same on the receive side, they have a pre-selector of some kind, and that goes down and down and down. But the duplexer itself only notches one frequency, either the transmit side for the receiver or the receive side for the transmitter, to get rid of descents and sideband noise from the transmitter in the other case. One last effort here was to couple these 2 units together, the bandpass filter and the pass reject filter, with the results that you see on the screen. We have a level that's about 1.8 dB down at the peak. We have a notch that's in the 44-45 dB region. And as you see, the tendency for these to be up in here has been dropped down so that you're almost 40 dB at 150 and about 30 dB at 140. So a much better improvement for those who are trying to use this equipment on a crowded hill with lots of transmitters above and below you.